Okay, I wanted to make this video in order to show you a few animations. So I think it's useful when you kind of see things that are moving, and we can explain a little bit about the different types of plate boundaries. So from the lecture and the PowerPoint, you can hopefully remember or see that there are three different types of plate boundaries that we identify. There's divergence, where they're moving away, convergence, where they're moving together, and transform, where they're sliding past each other. Now for convergent boundaries, we do have some subsets there, so three different types. So I just want to go through really fast and show you some videos and kind of talk you through it. So let's give that a whirl. So if we come over here and we look at a kind of a spreading center. So when they first figured out that plate tectonics was happening, they called these boundaries spreading ridges or spreading centers. This is where new crust was being formed, and a great example of that is in the very middle of the Atlantic Ocean. There's a divergent plate boundary, and so if we kind of take a look at that here, you can see it's identified by this red line. And so two plates here are being pulled apart. Now there's a bunch of reasons why that's happening. So when we talk a little bit about in the previous module about interior of the Earth, right? We have some movement of the material that's beneath the rigid lithosphere, and so that material is convecting and moving the material around, and so it's pushing the material apart here. We have some conditions that are met that causes part of the mantle here to partially melt. And so when it's a liquid, it is hotter and less dense than the surrounding material, which is a solid, which makes it buoyant, and it rises up and it kind of oozes out here where the plates are being pulled apart, cracked, and fractured. In addition, we talked about in the lecture, or you kind of read through the PowerPoint, that under certain conditions, when the magma or the lava is molten, as it cools, there is, because of the composition of the material that's being brought to the surface here, it has magnetite in it, which is a mineral that will align itself with the magnetic field. And so what they saw when they were kind of looking at this spreading ridge, right, they took some core samples across this ridge. Not only did they find some weirdness related to ages, that the rocks here at the center were very young and they got older as you move away, they also identified this striped pattern that was identical on both sides. And so they were using what's called paleomagnetism. This was something that helped them identify that there was new material being created here, and then as it moved away, we got this pattern here. Of course, it also told us something about the magnetic field, that it does switch or flip over geologic time. So this is kind of our divergent plate boundary, and like I said, the mid-Atlantic ridge is a great one. But we can also look at, let me go to the beginning of this one. How did that start? Well, it doesn't always start in the middle of an ocean, so sometimes we can have it start in a continent. And a great example of that is the Red Sea here. So here we are in Africa. You can see there's a small sea here, but the idea is that these two pieces of continental crust were once connected, and a new boundary developed here. This is what the Atlantic Ocean started out as. And so millions of years ago, the Atlantic Ocean didn't exist, but there was a change in how the movement of material was occurring in the interior of the Earth, and it created a new boundary. And so it started to pull or push that material apart, the continental crust. It thinned, and it got thinner, it broke, and as it was fractured and broken, just like in that previous video, some molten material is able to come to the surface. And so if we watch kind of how this would have developed, this is kind of an analogy to how the Atlantic Ocean was formed. So about 3 to 5 million years ago here, right, it was all continent. But here's this upwelling of material, and it's causing this continental crust to be pulled apart. It breaks, it fractures, it thins, and some of this molten material comes up and creates brand new crust. But now when this crust is created, it's oceanic. Can't create continental crust from this process. And so we develop ocean crust here, which is more dense than the continental crust. It sits a little lower, right, in the asthenosphere, and then that causes it to be low. Water can move in, and over time we can develop a sea like we have at the Red Sea. And if it keeps growing, of course, we can get a large ocean. Right? So this is how we view and describe a divergent plate boundary. So there's magma here, lava comes to the surface, there's a high ridge here, there's earthquakes here because we're cracking and pulling apart this crust. These are two of the ways that we can also identify that this is a boundary: volcanic activity and earthquakes, right? Okay, let's move along to this one. So another boundary when we talk about collisions is a ocean continent. So we did that divergent, now we're doing convergent. And a typical boundary that we see is between oceanic crust and continental crust. And a great example is here in South America. And so here we have, I'm going to view a side view here in a minute. Here's the oceanic crust and the continental crust. And the idea is that when these two things collide, the oceanic crust always loses. It is more dense than the continental crust, which means it's easier to push down into this kind of plastic or ductile asthenosphere. And so this process of moving this plate beneath the continental plate is called subduction. And so we're pushing that down there, and now we have another process, another way to generate molten rock. And so when you subduct, you always get molten material developing here for a variety of reasons. Once again, that molten material is less dense than the surrounding material. It rises to the surface, and then it can erupt as a volcano. And so we typically get a volcanic chain here all along where we have subduction. So once again, we can identify this as a boundary for earthquakes. So the collision is stressing out the rocks, causing them to break. That's an earthquake. We also get volcanic activity here. So volcanoes form along this boundary. That's another way that we can define it as a boundary. We jump over to here, we can have a collision between two continents. Now, how does that happen? Well, a good example is if we jump over here to where India is colliding into Asia here, Eurasia, the Eurasian plate. Now today, these are two continents that are slamming into each other, right? And so it's a boundary because there's earthquakes here, but it didn't always look like this. If we roll back the time like we've done in a couple of the other videos, we will see that the Indian plate used to consist of continental and oceanic. So right here is a continental crust and here is oceanic crust. It's still one plate. This is not a boundary here. This is what we're going to call a passive margin. There's no activity here, right? Where we have a plate tectonic boundary, we call that an active margin because there's activity happening here. But we have a collision between two plates. Because there's ocean meeting continent, what does that mean? It means ocean gets subducted. It loses that battle. So, right, it's being pushed underneath. So what does that mean? Well, we get earthquakes here. We also get volcanism because the process of subduction causes molten material to occur in the mantle. Once it's molten, it's less dense than the surrounding rock. It starts to rise and it can erupt as volcanoes. But as time moves forward, we see that all of the oceanic crust has been destroyed. And now I'm actually taking a continental crust and slamming it into another continental crust. The issue here is that that Indian plate that's now, right, continental crust does not want to subduct. It's too buoyant, right? It is less dense. And so what we get is this collision and this crumple zone where the rocks here are bent or folded. We shut off the volcanism because we said, look, we need subduction to generate magma. That's not happening. No more magma. So no more volcanoes here, but we still get mountains. Now we have mountains for a different reason. We can have volcanic mountains, right? Because those collide. We get eruptions. We build mountains that way. The other way we build mountains is through a process like this of collision. And so here the Himalayas, Mount Everest, why are they there? there's a collision here between two continental plates. That's what's happening currently, and that's what's driving the range that you see there, the Himalayas and things like that. And so, of course, if we had a ocean-ocean convergence where we had a collision there, we still get subduction because there's oceanic crust involved. And what that means is one of those oceanic crusts would subduct. And it's usually the older crust because that's colder and more dense, but there would be subduction there. So that is our three kind of collisions or our convergent boundaries, right? We have continent, continent, ocean, ocean, ocean. We looked at divergent where we saw the spreading center. And then, of course, we also have a transform boundary. Did I hide that somewhere? Let's see. Oh, I don't know if I have that one. Okay, so let me show you really quick then a hot spot. And so what we've figured out when we're kind of doing plate tectonics is we're pretty confident that we know where volcanoes form, right? Well, volcanoes form where there's a process that causes the mantle to partially melt. We know at divergent plate boundaries where the plates are being pulled apart, there's a process there that causes magma to form, can make it to the surface, and we have volcanic activity there. We also know that when two plates collide, if there's oceanic crust or lithosphere involved, we're going to get subduction, and that process generates magma, molten rock inside the planet and the mantle, and that of course rises, causes volcanoes. So those where we should get volcanic activity and volcanoes. But of course we do see volcanoes in places in theory they shouldn't be. There's no subduction, there's no divergent plate boundary. So the explanation for that is what's called a hot spot. And so the Hawaiian Islands are a great example of a hot spot. And what you're seeing in this video here is that there is a plume of hot material rising up potentially from the core, and it's stationary, it's not moving. But what you're seeing in the video is that the plate above it is moving because we know the plates move. And so what's happening is it's leaving its imprint on the crust here. In this case, it's little islands because there's enough volcanic activity to build up a volcano that gets big enough, it goes above sea level, and then voila, you have an island, right? And so as we continue to move along here, you'll see that the plate is moving, in this case, kind of to the northerly direction, at least in the geologic past, and it's leaving this chain of islands here. So as this kind of gives us an overview of the ocean floor, we can see that there's this little linear feature that helps us identify the direction that the plate was moving. And so if we look at this image here, we see that 50 million years ago, there's this line of islands being created. And so 50 million years ago, the hot spot was here. This line in this direction suggests that the plate was moving basically to the north, and it leaves behind this chain of islands. Now over time, these islands get weathered away and they go below wave base, and so they're no longer islands. But what we also saw in this chain is a different direction in the linear kind of island chain that we see. And that's a suggestion that the plate direction changed. And so in the end of this kind of chain here, we're going to see we have the Hawaiian Islands. And so here they are here. The current hotspot is here, developing more volcanic activity, right? But over here, these are underneath sea level. They're no longer islands. They have been weathered away, but they still exist. We can still see the remnants of it. So it helps us give us direction over geologic time. We can age date these rocks so we know when it was moving in what direction. And of course, as the plate continues to move, we will develop more islands out here to the southeast as the lava becomes large enough to go above sea level, and then we'll have a new island. And so, and there is one developing off the big island of Hawaii. And the islands that are farthest from the source are no longer getting new material. Only weathering and erosion is taking place. So over time, they will be eroded down and no longer exist. And so this is the explanation for how we get volcanic activity not at plate boundaries. And so hopefully that's kind of useful just to see some animations and go through the different types of boundaries. And then, of course, as you go through the PowerPoint, there's some additional information there. But I was hoping that these little video clips would be useful to you. So hopefully that's true.